Okay, good morning everyone. My name is Shi Wang, and they are my group member Wei and Jialing. And today, the topic of presentation is analysis on the graph partitioning for network-centric computing, and we are the group F. Here are the papers we studied during this research, and this is outline of our today's presentation. We are going to go through the introduction, edge cut, vertex cut, and the conclusion. In the introduction part, let's first talk about why we need the graph partitioning. As we know that in the real-world networks, the size of a graph network could be extremely huge, which means the graph database will be distributed into multiple machines, and the communication between these machines is going to be a problem. So we need a good partition algorithm which help us can reduce cost, reduce communication time, and reduce the traffic in order to improve the performance. And here are the two main approach of the graph partitioning. The first one is a K-way edge-cut graph partitioning, which partitions the graph into K parts with vertices are evenly distributed. And the second one is a K-way vertex cut graph partitioning. It partitions the graph into K parts with the edges are evenly distributed. In the part of edge cut, let's first do a quick review of the multi-level approach which we have presented before last time. It consists of three phases: the coarsening, partitioning, uncoarsening, and refinement. And the best combination for this approach is heavy edge matching, the greedy graph growing algorithm, and the boundary Cunningham-Lin algorithm. And as I just mentioned, that in the real world, the size of the network could be really extremely huge. Here's such a case for the Facebook. Imagine that you want to query the friend list of all your friends, and the old 98 ways to use your user ID, mode, and numbered n, which is predefined, and query all these machines to get all your friends. But the new approach is to have a better algorithm which can extremely increase the possibility that you and your friends are in the same shard, which can dramatically reduce the time, and use the shard map as an index to find your friend directly. And the Facebook introduced the label propagation algorithm, which they use a constraint they use a size constraint for each shard with the upper bound and lower bound, and then they calculate the utility gain for each node if it moved, and then orders these nodes according to the utility gain from the greatest increase to the least increase, and labeling them from 1 to k. As I just said, the fx is a relocation utility function, and in this function, the uij means if we move the number k node from the shard I to j, the utility change will be demonstrated by this function. And the fx is a total utility gain from moving the leading x node from I to j. Then the problem is to maximize the constraint relocation function, which is defined as follows, and it also should follow the relations between this upper bound and lower bound. And here, as we can see here, the Pij represent for the node that desire to move from the shard I to j, and the Vi is the size for the shard I. Si and Ti are the lower bound and upper bound respectively. Xij represent for the node which will move from the shard I to shard j. Here is an illustration of the label propagation algorithm. As we can see here, just take the shard 1 for instance. It should follow. It should be the size of this shard should be between this upper bound and lower bound, and the node moved from the shard 1 to 2 should be smaller than the P12. And another idea in this paper they introduced is a good initialization could greatly benefit the graph partitioning. And the Facebook used geographic initialization during their work. They use the average degree to calculate the cost function. As we can see, the function that the NC represents for the population of the city C, the DC is the average degree of the city. With the lambda is a weight parameter, which is defined as 1 divided by the average degree of the whole graph. And here is balloon partitioning algorithm, which is used to implement the graph initialization. It first calculates the cost for every city, and then assign the corresponding cost to each city. Then it's going to find the city C with the largest unassigned cost, and grows the balloons around it. And then afterwards, all cities with the non-zero remaining costs are sorted according to the geodesic distance from C. And eventually, put the city C with the shortest geodesic distance into the shard of the city C iteratively, until the shard reaches capacity. And it also should be noted that since edges in the social network are overwhelmingly internal to countries, so they add a negative distance reward to the city in the same country. And here is an example for the geographic initialization. As we can see here, the broken line is a country border, and if they sorted cities with the geodesic distance from C, and we can see here, this node to city C and this node to city C is not the geodesic distance could be different, but with the negative distance reward, and they were at this city but not the city in the other country. It will help the algorithm to finish computing in one country completely and then move to another country. And then let's talk about experimental results. For the limitation, for the sake of limitation, time limitation, I just choose the most representative part of their experiment. They evaluate their algorithm in the real-time Facebook's People You May Know service. And here are the three sharding approaches implemented. The first one is the baseline sharding. It's just use the old naive way. They use the ID mode 78. 78 is the number of the shards you want to get eventually. And the second one is the geographic sharding, which just simply use the geographical initialization with no label propagation. And third one, propagated sharding, is a mixture of the label propagation and the geographic initialization. And as we can see in the picture, that the y-axis is the number of machines queried per request, and the x-axis is number of machines. As we can see in the picture, that the black curved line is the approach of the baseline. It increased dramatically when the number of machines reaches 77, and on the other side, the propagated approach just keeps decreasing, and it queries about 9 machines in average. So we can see that the propagated approach has the best performance. And the average query time also gives the same result, that the once propagated sharding only costs about 55 microseconds. Thus, we can draw the conclusion that the sharding approach with the geographic initialization algorithm with the label propagation have the best performance based on the tests just mentioned in this paper. And this combination may be a good option for the distributed social graph partitioning, especially for the graph with they have the geographic information.
Thank you. So we can see partitioning is essentially for better future computation, but the partition itself can be overhead and can be time-consuming. And in this paper, the author proposed a streaming approach to partition the graph data. And the idea is to, instead of partition the data when you already loaded the graph on the cluster, we partition the data while we are loading. At the same time, we're loading the graph. And from the previous example, you can see the graph data set is huge. Like the Facebook example, it has more than 900 million users with average degree of 130. And to cut the edge or partition it, essentially corresponds to the communication volume required. And it's very expensive to move the data in the cluster. So, and another constraint is the data has to be loaded onto the cluster before you perform the partition. So the idea of this paper is partition the data on the stream. And the question, can we partition while we loading the data? So to support this streaming partitioning, the first question, how to load the graph. That this question matters because the input order really determines the performance of your partition. And we need a graph loader. This graph loader is nothing but a program to read your graph. And this program reads the serial graph data from disk onto the cluster. And when you load the graph, it makes decision about the location of each node as loaded. And the goal is to find close to optimal. We know that the good partitioning is impossible because we only see a part of the graph when we are loading and when we are partitioning. But we try to find the close to optimal. The challenge is, first challenge, how to pick the input order. And the interesting part of this paper is that the author design the streaming model, try to describe this problem and try to propose the partitioning. So for this streaming model, we try to simulate the two things. One is the input order, in what order we are going to read the graph. And then the second question is how to partition based on the input order. So we have this graph stream, and we run this partitioner. We make this decision while we read the graph. And so this is a key cluster, which we have key machines. And the decision is made when we choose one of the key machines to put the node. So the goal is to generate approximately balanced key partitioning. And for the graph load ordering, the paper is for the random order, and another tool is the BFS and the DFS. So for the partitioning, they also consider we may have a buffer size to run the partitioning. So here is the lower bound of the ordering, and for the adversarial ordering, in which you load every other vertex, and this ordering, you won't see any edges until half of the nodes coming to the partitioner. So it can compete with the key partitioning. And for random ordering, it's similar to the bursty paradox problem, in which you only see edges after square root of n. But for this DFS and the BFS, these are the new approach in the paper, because when you read the graph in the breadth first or depth first, you actually consider the connections between vertex. So this ordering, you can run some greedy algorithm to optimize the partitioning. And for existing streaming partitioning, usually people only consider the vertex. They hash the vertex ID and find the location. And they totally ignore the edges, the relationship between nodes. So the advantage is the data can be located fast. But disadvantage, you may count, k minus 1 over k fraction. So this in this paper, the author evaluated 16 heuristics on 21 data sets and compared the results with random hashing and with offline partitioning. So for the heuristic approach, the author chose this list of different partitioning, and for another 3 approach, they specify buffer size. And for the conclusion, we found that the best heuristic is the linear deterministic greedy, and get average improvement of 76%. And also we found that the BFS is a good ordering for all algorithms. So eventually we found that streaming graph partitioning is a really nice and simple, effective, and we can use it as a pre-processing step before we run the actual offline partitioning.
Sorry for that. Actually, thanks for my friends introducing several H-cut algorithm. But actually, there are another type of algorithm which is the vertex cut, by which we can divide the graph into several components with equal numbers of edges and minimum number of disjoint vertices. So what's wrong with H-cut, and why do we need this vertex cut algorithm? Well, by H-cut, we can deploy the workload of a machine. The workload of a machine depends on both the number of vertices and number of edges located in one machine. But by vertex cut, we can evenly distribute the edge data onto multiple machines, and so we don't really have to care about the impact of the power law degree distribution of a certain real-world network. So let's take a look at the structural balance vertex cut approach. The basic idea of this approach is to find the dominant node with the highest balance score iteratively. So the steps are as follows. First, we compute the all pairs shortest paths, and then we compute the min-max ratio by this equation here. And then we compute the transition matrix according to the min-max ratio we have just computed. And then once we got the transition matrix, we can compute the balance score through a eigen decomposition process of M, which is to find the eigenvector associated with the eigenvalue of 1, such that all the elements inside this eigenvector can add up to 1, and each element is just the balance score of each node. So during each iteration, we find the vertex cut on the dominant node with the highest balance score, and then we just, as this figure shows, we include all the nodes that can reach to this dominant node into one partition, and we include all the nodes that are reachable from this dominant node into another partition. Then intuitively, we find another 2 dominant node in the later iterations. Then we just include all those nodes into one of those partitions. Then by repeating this above steps, then we find the biggest partition until k partitions are found. So here is the flowchart of the structural balance vertex cut approach for you to get a better understanding. And this approach is called the optimistic strategy. And there are 2 types of different variations of this approach. Since the optimistic way has its drawbacks, that is to eliminate the vertices aggressively from consideration. And this causes the partition result highly dependent on the initial dominant balance vertex choice. So that's why we need pessimistic SBV cut. So as you can see here, in the optimistic approach, we remove all the gray nodes here around this central dominant vertex. But in the pessimistic SBV cut, we only remove those 1 degree exclusive neighbor from this dominant node. Since the node 1, 7 is on other source to sink paths, we cannot remove that. Okay. Then there's another.
It's still under a minute in your board.
Sorry.
The time is slow in your board, but for me it's been 3 minutes.
Sorry for that. There's another variation called balance recomputed SBV cut, and in this approach we try to recompute the balance score at each iteration for the remaining vertices. So the author also carry out a comparison between all those 3 strategies. So overall, the optimistic can generate the partitioning result with the lowest quality but with the minimum running time, and the recomputed one can generate the highest quality partitioning result with the maximum running time. But optimistic way never fails to reach to a final solution, but the pessimistic and recomputed one seems pretty hesitated to reach the final solution. Well, the author also carried out a comparison between this vertex cut approach to the multi-level approach. But before he carried out this comparison, we have to know how to measure the quality of the partitioning algorithm. So there are 2 basic criteria, which is called the expansion, which measures the cut size ratio, and also the other one is called the modularity, which is just what we have learned during the class. And that measures how unitive the nodes are inside a partition. So the author of this paper just made some slight variation to this expansion as well as a modularity for the H cut to make it appropriate for measuring the quality for vertex cut. Then we can see the result here. Oh, sorry. Before that, also the. Okay. The author also introduced a way to converting a vertex cut into an edge cut by just simply inserting some edges between all those disjoint vertices. And also here are the results. As for the running time, the multi-level approach is definitely the winner. SPV cuts seem to be quite time-consuming, but as for the quality, in most cases, we can see SPV cuts just does a better job. Okay, now let's reach to the final conclusion. After studying all those partitioning algorithms, what is truly impressive to us? First of all, making less before doing more. Well, recall the multi-level partitioning algorithm where we reduce the scale of problem during the coarsening phase before we carry out the actual complex partitioning algorithm. And the second one is called more implies better, but may also lead to less. What does that mean? Well, let's recall the geographic initialization for balanced label propagation. So in this part, we require some additional auxiliary information, such as the geographic information, to make the partitioning result with a higher quality and less running time. And perfect is impossible, but there always can be trade-offs. Well, let's recall the balanced label propagation algorithm, which is typically a community detection algorithm with no guarantee of the size of the partition. So that's why we have to define the size constraints with lower bounds and upper bounds of the partitioning size. And the other one is called the streaming graph partition, where we were provided with 16 heuristics for us to carry out different trade-offs between the partitioning quality as well as the running time. And the last one is called think of the box, because usually when we considering about the graph partitioning algorithm, what comes into our mind first is the H-cut case. But vertex cut just gives us a new perspective to look at this graph partitioning algorithm problem to minimize the impact of power loss redistribution to the distributed computing system. So finally, when we're considering applying all those partitioning algorithm to the distributed network-centric computing system, what we really have to take into account.
Sorry, but we really need to cut it.
Okay.
Because we are getting into the next class.
Sorry for that. So the first one is called performance. All we have to care about is the performance, so that's why I need a streaming approach. And the second one is called we prefer less intercommunication between machines, so that's why we have to minimize the cut size and boost the data locality. And also, we have to be balanced. As for the quantity of data, both H-cut and vertex are qualified to evenly distribute the data over multiple machines. But as for local computation workload and storage occupancy, vertex cut just is the winner. So also, we have to be deterministic, which means once the graph is partitioned, we have to make sure that the data is easy to locate. So that's why we prefer a amazing hash function or deterministic greedy algorithm, or maybe we can just store the result of graph partitioning algorithm into a shard map. Okay, that's all.
I'm excited.